Okay, thanks for being here. Can you hear me all right? Can someone give me a thumbs up or something? Lovely. Thank you. Appreciate it. Um, if you're one I open this up to anybody in 126. So if you're not one of my normal students, this is an informal question session. I'll say a few words at the beginning, and then we'll switch over to your questions. I'll probably need to share this again, but I'll do it now. Copy this. I'm going to share a couple things in the chat so that everyone has access to everything. And let me know if it works or doesn't. If it doesn't, there might be nothing we can do. But that's the OneNote that I just shared. And then this is my exam archive. Um, and I have plenty of other things. Let's do one more thing to share. So if you go here, believe I have a playlist of just 126 exams. Let's find those. 126 exam prep. Yeah, I don't know why sometimes it makes someone request access. It might be if you're not in my class, I'm not sure. Um, anyways, so if you did, I probably will have to check email later to do it. All right, so let's talk here. So for if anybody's not in my class, whatever your instructor says about the exam is the rule. So if you're in Beckiel or initial first class, do listen to them. If I say anything different, their word goes. But I do want to tell you some rough structure. This is what I've told my students, and then I'm going to point to a couple things in case you need questions. While we're doing that, I want you to prepare your questions. Look in that exam archive and get ready with a few particular things. But I want to plant the seed in your head of a couple things. So for me, my first exam didn't include 13.4 acceleration. So I might have a small question on this. That might mean compute the tangential or normal component of acceleration. It might mean go from acceleration to velocity. You can find a lot of those on the first page of a lot of my old tests. I might have something on that page that talks about working with surfaces and computing partial derivatives. Page two will definitely have partial derivatives and possibly tangent planes. You might have to do a product rule, a quotient rule, a chain rule, an implicit differentiation, those sorts of things. So if any of that bugs you, find questions on the old exams. I typically always have something to do with local max and min somewhere. This is I just sort of hand wrote my review. I mean, I have on my webpage, I have lots of review material. You can also find um, that there, but know how to do this. Know the so-called, what I like to call the tree method, how to organize your thinking to find critical points. Um, then we're going to switch to doing things of should we learn how to differentiate related rates? Nope, there's no related rates, but there is. I Let's make sure I understand what you're asking, Brandon, because implicit is not the same as related rates. Um, but we'll get to that when we look at some questions, I think. Um, So let me keep going and then I'll peek at the chats here in a second. So 14.7, I typically ask one of these two things, either an absolute maximin or an applied maximin. There's usually not space to ask both. I really do it at random. Um, when it comes to the applied maximin, I would know the homework. And then we switch to double integrals. And that's been kind of everything with double integrals is the same as I've been explaining it, kind of the same process. We should know how to set up double integrals. We should understand how to do them in terms of X or Y. There'll probably be something where you have to think in terms of X or Y or reverse. On the last page, that will continue. And then I'll have something to do with polar. Okay, so there's my quick recap of the ideas. So yes, there can be optimization. I think that was a question in the chat. But to me, when I think of applied max and min, it adds a layer to what we're doing here. We have to set up the function. All of these things, I'm going to point to a couple things because no matter what we do, we'll make many people unhappy. We won't get to all the topics. But let me pull up one thing here. So first off, my materials page is always a good place to go. If you find at any point you're having trouble with something in chapter 14, I've got my notes here. These test preps go through these topics in quite a bit of detail. I have review material here. Here's my full review of chapter 14. So if you just want my version of a note sheet, how I think about absolute max and min, how I think about applied max and min, some of that stuff I handed out in class. Chapter 15. So if you need more practice with polar, I've got a whole group there. If you need practice with reversing the order, I have practice there. If you just need a recap of how we do those, that's there as well. So it's all on my materials page. You search for Andy Lovelace. Of all the Andy Lovelaces in the world, I have the biggest website. Beyond that, as you realize there's something you want to review, and I have to always say that most important, you should work through a couple of exams on your own and then grade them. Like put yourself in a real exam situation. That needs to happen at some point. But then when you find out you're struggling with something, you come here. So I have little snippets. If you're saying, okay, I don't know what to do with applied max and min, it's in my exam archive. So I made these where I do a few problems of each. But right now we're trying to help you diagnose what the problems are. And if you're going through, in recent years on old exams, I always do a little video. Now I do a video for each page. So that's the takeaway. Hopefully, we're searching a bit. We're doing a little panning for gold here. What are the things you might need to review? So that's my agenda. So what I hope you will do in a moment is choose some exam questions. And it looks like I did not copy all of them over, but I can add them in quickly. So it'd be nice if you said one of these exams. I would like to focus first on exams by me because this is mostly for my students. But if we run out of questions, you can ask me other ones. So I'm about to open the chat. I'm going to ask you to blow up the chat with old exam questions. I'm going to keep a little list here, and then we're going to kind of look at the list and try to pick through some of them. So give me some questions. And then as we do, we'll do my little tour of exams as we go. So particular old exam questions is what I'm looking for. Lovely. And I'm just going to write a few down and then I'm going to kind of take stock and then we're going to go. So I see a fall 18 number 4. I see a winter 24 number 4. Keep them coming. I see a winter 24 3B. I see a fall 23 number 4 Jisoo Su, so different instructor. What else you got for me? Okay, oh, I missed one. Spring 19 3B. Winter. And we'll get going here in just a second. I like to just get a collection of things, see if we have any common exams a lot of people are asking about. Any last ones to add to our initial list? I suspect a lot of those are like global max and min, now that I look at what's being asked, or double integrals. There was another one. Winter 24 number 4, spring 25 4B. Okay, this list isn't too long. Let's look at because the winter 24 was mentioned a few times, I'm going to start there. So we're going to look at winter 24 and then see where that takes us. Okay. Any general questions before we get going? So let's do 3 minutes of general questions. Anybody in the chat? So one general question was, could optimization be on there? Yes. So we just mentioned that already. Do you get a node sheet? Yes. All right, let's go then. Winter 24 is what I'm going to pull up. And for better or worse, this is what I like to do. We are going to take a quick tour of the exam because it's the first exam we're looking at here. At any point, if my like mic cuts out or something, someone let me know in the chat. Okay, so this is winter 24. Let's imagine we were a student that term. Oh, and I apologize. There might be some writing because some of these I copy from quarter to quarter. So the first question, and we're just going to glance at it. Now, you should work some exams in detail, but we're trying to get to question four. Um, Tangential component of acceleration. So let's say in the chat, just think about what your very first thing out of your pen or pencil is going to be. If, let's just say, if it was asking for the tangential component of acceleration. So run that through your mind briefly, because it's nice to play this game as much as we can. Yeah, you're going to find derivatives. So this question would be find derivatives. Find when they're orthogonal. Ultimately, it means this is going to be zero. But anyways, let's keep going. That wasn't what the question was. Then there's some partial derivatives. I actually remember that this problem was hard for quite a few students, that there were a lot of mistakes here and here. So there's a partial derivative question. This wasn't asked, but I remember the year I gave this exam that both of these had quite a few errors. And it's kind of one of these things where people tend to study something else they're worried about, global maximin, applied maximin, and then they miss the foundational thing. So, and this was kind of tricky. There was one part in here that was kind of like a homework question, but this is a fairly quick question. So let's just very quickly do it. I know this isn't what you asked. I'm never going to Dr. Lotus's review session again. He doesn't do the questions we asked. Is there anyone here that's not from my class? Thumbs up if you're from another class. Oh yeah. Well, this will be the last time you probably come. Um, Here we go. So partial with respect to x. X is our variable. There's only one x in each term. So back when I taught this, I said the sums come along for the ride. Then we have three jobs. This job, this job, and this job. Since the variable is x and y is a constant, y is actually a coefficient. So now we've broken it down into three much smaller jobs. I need the derivative of y to the x with respect to x. I need the derivative of sine of x squared y with respect to x. And I need the derivative of log of x. The one that was kind of, I don't know if I think that quarter, so many students asked me about this that I decided to put it on the exam because it was in the homework. What's the derivative? Who can tell me quickly of y to the x with respect to x? That's more of a homework question. It's close. It does have a log in it. So again, I normally wouldn't ask that because it was on the homework. It was fair game. It was a small part of the question. Most students did all right on that. Probably the most missed term was the next one, was this, if I remember correctly, when I graded this. So the derivative sign is cosine x squared y times the derivative of the inside. So what's going to go here? That's kind of a hard question because you might want to be, you're probably wanting to answer this question down here. So by far, this was the most common error I remember in grading is people forgot this y. So this ends up being 2xy times the y that was already there. And so it was y squared. And then the last term is 1 over x. So there were a couple things that I think when I wrote that question, I remember I graded this one. I remember thinking, "Oh, I didn't mean to fool people, but I did." Okay, and then if you do the derivative with respect to y, there's a y here. There's unfortunately two y's in the same term here, and there is no y in the last term. So we need the derivative with respect to y. The fact that there are two y's in a single term means we need the product or quotient rule. In this case, that's the product rule. So let's see, it's going to be bring down the power and subtract 1 plus, and then we get to play the product rule game. First, second, first times derivative of the second plus the derivative of the first times the second. That's what I'm trying to write here. So first is y, second is sine of x squared y plus, and then just to so you have something to do in the chat. What's the derivative of the second with respect to y? So just the derivative of this. Tell me what goes in this spot. Very good. Yep. Owen wins. It's close though. And then the derivative with respect. So the derivative of the first. What goes here? This one's easier to type in. It's a one. Yeah, you don't have to actually write one. So, anyways, I like to mention that because this will happen. I mean, this is kind of a big one. I found that a lot of people missed a point on this part and missed a point on this part, like made an error in both of them. And that was I remember when I wrote that question, I was like, oh, I didn't expect that this would be a reason people would lose a couple points. So good for us to review. Lovely. The second one's implicit. So this kind of goes to Brandon. You were asking about related rates. I wouldn't call this related rates, but this is implicit. So I know I haven't gotten to the question yet, but when I happen upon something I know is valuable, we stop. So what about this one? Questions here. Do you want to see one C? Do two people want to see one C? That's a one. We need another. Oh, sure. Okay. So this is one C, and I forget. We're in the winter 24 exam. So when we do this, the point of these questions isn't that we need to be an expert on implicit. Implicit's pretty valuable. But it's that there's actually two variables when you do a partial derivative. There's the input and the output. So the way we think about it, we don't usually write this, is we say, now we're going to treat z as a function of y, but we may not be able to solve for it. So in our head, we're thinking z is a function of y, but I can't seem to get it by itself. And then I have y squared. I have z as a function of y, and then I have this. So this is really just helping you get the role of your variables. So there's a variable here, there's a variable here, there's a variable here, there's a variable here. This is not a variable, this is a constant. So that's why we ask these questions to make sure you know what this collection of symbols means. And that collection of symbols means z is a variable, it's an output, and y is a variable, it's input. So anything I underlined has to be differentiated. Okay. Now, once you get comfortable with this in Calculus 1, we don't do this and we don't actually write the function. Okay, that's the idea of implicit differentiation. And then we use the clever idea of, well, if something's trapped inside of something else, we can use the chain rule, right? If I were to give you cosine of x to the third, we know how to take the derivative because we take the derivative of the outside then the inside. Okay, so let's do it. So here's how it would go. We're going to differentiate with respect to y, treating z as the output. So z is being treated like a variable. So you're going to write 3z squared. That's the derivative of the outside. What's the derivative of the inside? So now we're going to write dz dy. That's the derivative of so this is the part that's the implicit part. Then we're going to write plus, and this is probably the toughest part of the problem. There's two variables here in the same term, so you've got to use the product rule. Boy, I was mean. I had two product rules in a row. What a jerk, that Dr. Lovelace. Okay, y squared. We're going to do the derivative with respect to z. So I'm going to leave two things blank just to see if you're awake. So think about what goes in these spots. I'm going to erase this for space. I was just explaining. And then I'm going to write equals. And then I'm going to write x. And then I'm going to become a calculus. Calculus students like to write things in ugly ways because we can use our rules more easily. So when I look at the problem, I think x is a coefficient. So I just brought it down. It's a number out in front. And now I have three little derivatives to do and I'll be done. So three little derivatives. The derivative with respect to of z is 1 dz dy. The derivative with respect to y is 2y. The derivative of this mess is 1 half 3y squared to the negative 1 half times 2y, also known as y. And then I like to say that the moment I'm done taking derivatives, I like to turn back into an algebra student, meaning I would probably simplify this a little bit. I would say, well, both of these are times dz dy. And just because I don't like negative exponents, I would rewrite it this way. That's not necessary at all. But I like to distinguish. When I'm doing derivatives, I like exponents and fractional powers. When I'm plugging in numbers, I don't. Now, this question didn't say you had to solve for the derivative. What did this question say you needed to do? This is an important little comment when you're doing messier numerical problems. If they're just asking you for a value, you do not need to simplify. You just need to plug that in as soon as you can. So I would plug in a 1, 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 and see what I get. So that's going to give me 4 dz dy plus 2 equals 1 over the square root of 4 for a grand total of 4 dz dy plus 2 equals a half. Dz dy times 4 is negative 3 halves, negative 3 eighths. Somebody verify for me if that matches. Does that match my answer key? That doesn't mean it's trustworthy. It is my answer key. Okay, so there's the game. If you want a more complete discussion, I think I have a video on that one in my exam archive. Lovely. Somebody was asking me a part A, but I want to honor the fact that that wasn't the original question, so we'll kind of put a pin in that. Um, let's kind of keep looking. So I just like to do tours here. I think I am going to fast forward to questions 3 and 4, but in your head, you should be thinking, find and classify critical points. We should have a plan. Partial with respect to x, partial with respect to y. Simplify one of them. Doesn't matter which one, usually whichever's easier. Substitute into the second one. Solve. So we kind of have a certain plan for how those go. Let's keep touring. Uh-oh. Reverse the order. So this is about relabeling this graph. So this entire problem is, can you label this? Can you label that? The bad news is I think the pattern changes out here. So this question is all about labeling. How did I know it's relabeling in terms of X? Well, it was given in terms of Y. So that's a game we can play. I'm certain we could spend the whole hour talking about that. Um, then we have some volume setup questions, which unfortunately I've written all over. I'm going to erase. This is the last quarter I taught this. So there's a volume setup. We definitely like to have a plan for those. We have a polar one, which was the question originally asked. And we have a global max and min question. So I think let's do the polar because I think someone asked the polar question. Is that correct? Is that person here? Yeah, 3B. This is of winter 24 polar. Okay, so let's make this a little bigger. I'm sorry, I realize my sizing is not good here. So this is the area of a polar region. This feels a little like one I did in lecture, but let's recap the idea. So the reason this is here, because when you see area, you think, are we back in Math 125? But we never learned how to do area of polar regions in Math 125. So what is, everyone help me here. We'll break this up. We'll introduce the non people that aren't with me to my four steps of every single math chapter 15 question and the things that we're thinking about. So one is what's the integrand? And there is a way to do area with a double integral. So for my students or anyone, what do we put here? Yeah, one. We talked about that in class, how integrate doing a double integral of one is the same as finding the area of the region. And the reason we're doing this for polar is because we never learned another way. Step two is to draw the region. So first we find the z's. They told us that. Second, we draw the region. They gave us that. Third, we give the bounds. So this question is really about the bounds, and most of these questions are. So in order to figure out the bounds, we have to do things in polar. The reason we have to do it in polar, I shouldn't say have to, maybe I don't want to convert this to Cartesian. It's already given in polar. If we're struggling with what that means, this curve, this means R always means distance out to the curve. So let me show that here. So for example, if you were to plug in zero, this is not part of my solution. I'm just making a comment. What is 2 times cosine of 0? That's a weird little question for the chat, but it's 2. How do we graph that? What does that tell us in the graph? So think about what that tells you. It tells you that the distance from here to here is 2. The reason I know that is because it's angle 0. So this point right here I know is 2 comma 0 in Cartesian, but I knew that because I plugged in a 0 there. I'm only saying that to emphasize that when we write r of t or r of whatever theta, it's the distance as you walk out. It's also true when you go a little ways away. So if you walk from here to there and someone tells you this angle, then that's also going to be 2 cosine of 3 theta. So 2 cosine of 3 theta is how long you have to walk to get to the edge of the rows. So I want to make that point clear. That's important because that's one of our bounds. It's the outside. When you walk towards your region, you eventually touch right here as well. That's the inside. So I think of these as inside-outside problems. So our job is to find starting angle, ending angle, inside, outside. So let's play that game. So we need four things. Start angle, end angle, inside, outside. Okay, what's the starting angle? Let's start rotating like a little radar detector. When we get to the region, we hit the buzzer. Eh, zero. So starting angle is zero. In terms of our bounds, we can sort of play this fill-in game as we go. That means there's a zero here. The ending angle, we don't know yet. I don't know what it is. It's this place whenever we get right here. So that angle I need to find at some point. But that's going to be when these intersect. But that's confusing because one of them's in Cartesian and one of them's in polar. We need to convert something. Probably better to convert to polar. That's something I find that people don't always do because we're kind of polar is new to us. But if you realize it's a polar question, immediately convert everything to polar. So what is that in polar? That's r equals 1. So if I need the ending angle, I need to know when these two things meet, which is this. And there's a whole bunch of answers. And now I get to think about the unit circle. Where on the unit circle is cosine of blah equal to a half? So in my mind goes right here, there, and here, because that's when the x coordinate on the unit circle is a half. So there's a whole bunch of answers, and those answers are pi over 3, negative pi over 3, and many repeats. So that's how I think through it, but that's more than you want to know. Okay, so 3 theta could be one of many things. Negative pi over 3, pi over 3, and many things to follow. Which makes sense as there's lots of answers because there's lots of intersections. We just want the first positive one. So then I divide everything by 3 and I get theta is negative pi over 9, and so on. So it's kind of weird because we don't see that angle very often, but what is this angle? It's pi over 9. Yeah, we don't get to work with pi over 9 very often. Okay, so that was a tricky part of this. We okay there? Questions on that? The rest of it is that's probably the hardest part we just did there. Well, the integration, maybe I haven't looked at that yet. That was probably the hardest part of this problem is finding the intersection. And hopefully you see why we needed it. The other parts are actually quick. I basically already said it. So now I think if I'm between these two angles and I start walking out, when do I first, when do I exit the region and when do I exit it? I said the same thing twice. When do I enter the region and where do I exit? So I enter it when R is what? 1. Yep. And I exit it when R is 2 cosine of 3 theta. And then the most important part, so if you're not one of my students, you might not have heard this, but whenever you do polar, and it doesn't matter if there's a 1 here or anything else, you have to finish by talking like a pirate. You have to say R d theta. I say that to be ridiculous, but also it makes it hard to forget. Um, there we go. Success. So, any questions on setup there? That was really the challenge. There's a separate challenge in evaluating because I can see just by peeking ahead, you're going to end up having to integrate a cosine squared, which I can review, but there's a place where you're going to need to integrate a cosine squared. How do you integrate a cosine squared? So somewhere down the line, you end up with a cosine squared of this. What's your next maneuver? Half angle, yeah. So I could show some of those details, but we've made it through the worst of it. How are we doing? I think Aiden, did you ask this? Are we all right? And I want to make sure I have my audio on. Someone's unmuting. See, Aiden's unmuted, but I don't hear anything. Could be that. Okay, great. Thanks, Aiden. Let's move forward. There were two people that asked about question four. I do already have written solutions because I did this probably many times in previous terms. Um, but it's a global maximum question. Part of the thing is, if you look at solutions to global maximum, they're going to look crazy. It's going to look like the biggest, scariest thing ever. But it's really a short bit of things. So I want to do a few things to get out of the way before we get there. Um, Sometimes I think I sometimes jump past this, but I think sometimes that just looks scarier than it is. So that's describing a region. So take a second and think about if you can draw what that region is. It's not meant to be confusing, but if we're new to set notation, that's just describing a region inside the circle of radius 5 and above when y is positive. So when I read that, I go, okay, they want inside the circle and when y is positive. They want the upper half circle. I say that because I sometimes blow past that and I realize that was the actual question. So don't let the bright lights distract you here. That's what that's telling you. And the moment you draw that, you actually know one thing about global max and min questions is we know exactly what the whole thing looks like. The moment I draw this up, I know what the entire solution looks like. It's kind of like you get just to turn the crank on the mouse trap. There was going to be three jobs. Inside, the lower boundary, the upper boundary. So if we scroll down to the solutions, that's what we're going to see. So let me break it down. I think I won't rewrite it. I'll grab a few things, but let's see if we can read the solution that I wrote in a previous quarter. And I'm going to tell you one thing about these is if you think about grading, I mean, I don't love grading these, but the things I look for are this. Did the student consider the inside? Did they try to find a critical point inside the region? Did they describe what it means to be on the boundaries? And did they plug those into the function? So the reason the solutions are always look big is because there are multiple steps, but those steps are pretty well laid out. Um, let me, so let's fill in some of the details. Get rid of those little dots there. Okay, so first, let's go from there to the next step. So I found the derivatives. When are both these zero? So this would be zero when x is zero. So then you take that and you shove it into this equation. Sometimes that bothers people that there's nothing to shove in for. It's perfectly fine. You just continue solving. So I think you get y is -4. So there's only one critical point that could possibly be in the region, and it's this one. And when you look, it's not in the region. And this is something that is easy to miss, but often more important than finding the critical points, it's finding that there aren't any others. So we're reducing the number of things we have to check. Within the region, there is nothing we have to check. That's very helpful. So then we say, what does it mean to be a point on this side? And if I hand you a point on this side, there's something you can say for certain that y has to be 0. You can actually say more. You can say x has to be between -5 and 5. So then it turns into a one variable calculus problem, which is what is the biggest the function can be if you plug in y equals 0 and x is between -5 and 5. Now, for my students, they know that I like my Calculus 1 global max and min, but the bad news about these is you have to kind of like that, meaning the problem boils down to this problem. How do we find the global max and min of a one variable function over an interval? So that's one problem that needs to be done. Then you do the same thing for the other boundary. So if you're standing on the other edge, you're on this circle. So you plug that in, you play the same game. That gives you another function. Ooh, this is a bad one. And so to finish this problem, you'd have two one variable calculus problems to do. So let's just talk about layout first. So that's what a global max and min question looks like. We're not done yet, but those are the key components you know are there. If I was grading this, I would need to see the function above one side, the function above the other. And now we have some work. I think this is just unfortunately not the nicest one for the next piece. So now when you get to a one variable calculus problem and someone asks you the max and min, that always involves plugging in endpoints. And there are two, -5 and 5. In fact, let's just do this. And you actually, the endpoint gets, you don't need to plug it in twice on both edges. You can do just once. And then you need to take the derivative, the one variable derivative, and see if it's ever equal to 0. So to me, I compartmentalize. I know for a one variable function, I need to plug in the endpoints and I need to find when the derivative is 0. Oh yeah, it might have been easier to set X. This is when it's bad that I'm using old solutions. I might have done that because, well, I might have done it because I'm not very smart. That's one reason. But another reason could be that a student was asking me about that years ago. So yes, you could, well, yeah, there's plenty we could talk about. But if you prefer, you could solve for X and substitute that in. That probably is significantly easier. If you choose to use Y, though, then you need to say Y is between 0 and 5. Those become your bounds. So I could spend some more time here, but I think it's good to just talk about the general outlook. If this is something, because this is kind of a big topic and easily can bog us down, I would go to, can you see this and make sure I'm sharing this? I would watch this, where I do several of these problems in a row. Probably better than me continuing here. And then the other thing that might be useful is in my chapter 14 review. I do a handful of these. I think in this test prep, I do one of every type. So I do local max and min, applied global max and min, applied max and min. So you can see me work through several. Um, okay. I don't know if that was great, but it was something. So we did winter 24, 1B and C, and that was partial derivatives, and one of them was implicit. We looked briefly at a couple other things. This is I'll go through this and add timestamps later. I'm just making a little commentary. We toured the rest of the exam, then we did a polar question. And then we did half of a global max and min question. And I hope we got something sort of out of that. But I know that whoever asked about four, I didn't fully handle your question. Fall 18. Okay, so I think I'll switch because the person who asked about fall 18 just asked a follow-up on that. So I think I will jump over there. But how are we doing? Is that all right? We get anything out of that? Okay. It's like it always feels like I'm talking to myself, so I appreciate that feedback. Um, can we do 1A of that test? So there was a question about 1A. I think it's fairly quick. So let's do 1A before we completely erase, because I've had a couple of people mention that. Sometimes people do it publicly in the chat, sometimes people do it privately. And then we're going to move on to Fall 18 because that person was on first, and we'll tour that exam a little bit. So before we leave this land, I think there's probably a little bit of algebra that might be getting you here if this question is not going your way. So we're still in winter 24, but we'll wrap it up here. Um, this question is kind of a couple different things. It's hard to ask very much from 13.4. So it says, find the positive value of t at which the acceleration vector and the velocity vector are orthogonal. So here's the velocity vector. And then, uh-oh, we need to take the derivative of this. And calculus students like to write it in this ugly way. So we get negative 2t to the negative 2. And now we're going to do the second derivative. So here's the velocity. Here's the acceleration. Everybody with me there? So the question says, when are those orthogonal? So what do we need to do? There is something that's zero. It's not cross product. It's actually better than cross product. Hmm. Sorry to chew ice. Okay. The dot product needs to be zero. So this question was asking, when are these two perpendicular? That actually means something. It means your acceleration points straight inward. Um, we used to do more with this, but when we think about acceleration, so the velocity points in a way that it's tangent. The acceleration can point in front or behind the following two vectors. So I'm not going to ask explicitly about these vectors, but they're useful in our thinking. Sometimes the acceleration is in front of this, which means you're speeding up. Sometimes the acceleration is behind n, in which case you're slowing down. And sometimes it points directly inward, which is what this question is asking. So this question is asking basically, when are you not speeding up or slowing down? But you don't have to think about any of that. You just mechanically do it. So dot product, dot product, dot product. Let's do it. So when I do the dot product, I get 4t plus 6 times 0 is 0, plus whatever these two things multiply. So one challenge is you have to check your algebra here. What in the world is that? Always like, so this is where calculus students write things in ugly ways. If I'm ever unsure about simplifying, I rewrite it in a non-calculus way. And if I still am unsure, then I write it out. I'm always pleased on the final when someone writes all of them out and counts. There's five. Oh, yeah. So it's negative 8 over t to the fifth. And the question's asking when that's 0. And this might be where the challenge was. And this brings up a story. Um, one of my An observation I made years ago in teaching calculus is that if I put this question, just a small detour, please forgive me, but I have learned that if I put this question on the final, most people get it right. If I say give all solutions to that, most people get it right. Sometimes people forget the negative, but most students get this right. I have a point to this. And then I learned over the years that if I put the following question on the final, a large number of students get it wrong. And that's interesting to me. Why is that interesting to me? So why do most students get this wrong and most students get this right? And it pertains to what's about to happen when I go back to that problem. There is something about this that bothers us visually, I think, as algebra solvers. This looks weird to us. And the point of me saying this is the reason it looks weird is because there's a variable in the denominator. And so you have to have this idea that the moment that happens, get rid of it. So how do you get rid of it? You multiply both sides by the denominator. This is a very important algebra skill is clear the denominator. And when you clear the denominator, it becomes the exact same question. So I've done that many times where this I find even advanced math students have trouble solving this when it's actually the same as this. Um, okay, so back to our problem. Back to our problem. Why am I saying that? This looks weird to solve. It looks weird because there's a t to the fifth on the bottom. So what do I need to do? I need to multiply by everything by t to the fifth. That's it. And if you're having trouble solving that, you just fell into that same trap of it looks worse than it is. I've had a few students tell me, well, that wasn't what bothered me. You're wrong again, Dr. Lovelace. Okay, so I've had a few students say that what bothered them is they didn't know how to solve from here. Now, the question asks for the positive time, but you'd have to say 2 to the 1/6 or the sixth root. That's it. The second part of the question was supposed to be an immediate consequence. I remember when I graded this test that there were some mistakes here. Um, where people spent a bunch of time computing these and then plugging this in and solving. But since we already know the top is zero, you don't need to do any work. You can just say zero. Does that make sense? Does that answer that question for whoever was asking it? So pretty much any question I ask about 13.4 is a computational question. Other things, can I move forward? Hosti, did I get your question? Sorry if I said your name wrong. Yeah, great. Somebody's asking what could I ask about 14.1? I kind of answered this in a discussion post. So I might point you there because I that's a more thoughtful answer than what I'm about to give you. Um, but in the past, I've asked an occasional question about give the domain. I've had a very rare question on like think about a contour. But I think about 14.1 was more just gearing us up to use it in later sections. So it is harder to ask directly about that. Um, let me get back on track here. So I'm just going to add this winter number 1A. We did 13.4, I'm just going to say. And now we're going to head over to fall 2018. Thank you for your patience on this one. So here's fall 2018. Get rid of this. Fall 2018. Oh, there's another one of these questions. So, now that we've seen it one already, consider this, find all values of t at which the tangential component of acceleration is zero. So this is almost identical to the last one. The hard part on this test question was students got stuck right here solving because they didn't clear the denominators. Find the tangent plane. That means you're gonna have to find the partial derivatives. That wasn't what the question. Oh, find the volume under this and above that. So we could come back. There's a volume setup question. There's a polar question. There's reverse the order. There's a global max and min. Ah, thank you. And then there's this one. This was a homework question, but a homework question that um, easy to struggle with. So let's talk ourselves through it. And I'm on the right one. Is that correct? All 18. Malik, was this one you asked? Did anyone, do you guys want to see this one? I'm just, yeah, okay, great. Um, good. Okay, I was just making sure we were here. Um, so this question is a generalization of something you did in Math 124. If you took Math 124 here, in Math 124, there's a problem where they give you the equation of a line and they say you're allowed to draw a rectangle under it anywhere you want. And the question is, where do you get the biggest rectangle? And that's an optimization question. This is the 3D version of that. So now we're going to give you a plane and we're going to have you draw a rectangular box under it. So it's really complicated when you think of it that way. Yeah. Find the XYZ dimension of the rectangular box with maximum volume. So for me, all optimization questions, I have the same approach, whether it's Math 124 or Math 126. I find these words, and that becomes the guiding light for the entire problem. So I know what the whole problem is going to look like the moment I read those words. I'm going to write volume. I'm going to somehow get a two variable function. I'm going to find the critical points, and I'm going to make a conclusion. So that's how so this was kind of this adds a layer to it's mostly about finding critical points, but there's this layer you have to get through at the beginning. Okay. So let's talk through those pieces. So any question that says minimize the surface area, minimize the distance. It's very important you identify that that's the only thing you're going to take the derivative of. We're going to construct a new function that represents the volume. And then we're going to find where that new function has a lowest or highest point. Okay, so volume of a box that's sides x, y, z. So the volume is x times y times z. And you immediately run into the problem, which is that we want a two variable function, but we don't have one. So the question doesn't make sense yet. There has to be a constraint. Because the goal is to maximize the volume, just make it infinite, make it as big as you want. But there's something that's restricting that from happening. So there's always another piece of this, which is the constraint. Something that's constraining us, something that's giving a relationship between these numbers so they can't be picked to be anything they want. So I have learned that, I mean, this is bad. I'm teaching you bad habits. You need to read the whole question, but I've learned that I only need to see those two words and then I know how to do the entire problem. That's true for a lot of optimization problems. Like the moment I see those words, I mean, I always read the whole question, but then I start to look and see, are there any equations here that have to do with X, Y, and Z? Oh, right there. I see it. Okay. 4x plus 3y plus z equals 12. Can I solve for this? So I can kind of turn myself on autopilot. in terms of setup for all these problems, the moment I recognize what the maximum or minimum is. Okay. So that's kind of the big idea. There's a separate issue here, which is the algebra is not, it takes a little bit of care. But the reason I say it that way is it's very common on these tests that I'll see students do this and then they'll start taking derivatives of this. I've seen this a lot on exams. They'll write -4, they'll write -3, they'll set this equal to 0, and then they'll say DNE, and then they'll move on. And that's tough because they're not going to get very many points. So the only thing you're going to take the derivative of is volume. So it's very important you write that in step one. Okay. So let's now go through the details. I always spend too much time there, but I do think it's very important you have this plan. All optimization questions. Find what you're optimizing, write it out, and then plug in your constraint. Okay, so now I'm ready to do the problem. That ends the applied part of it. The rest of it becomes critical point work. So we have the volume equals a function of two variables, and it's x times y times 12 minus 4x minus 3y. And now I've done it. I like in my head, I go, is this the volume? Okay, now I'm ready to differentiate. Here's where things usually go wrong for people. You have a choice here. You can either use the product rule to take the derivative or you can expand. It's almost always better to expand when you're taking the derivatives. So I'm going to expand it out. So any questions so far? That kind of ends the setup component of this problem. We good there? A thumbs up, a thumbs down, a frown face, a smile, a party emoji, anything? Okay, that's good. Okay, so the next part is the derivative with respect to x and the derivative with respect to y. I want to go a step further because there's a moment that will happen in a second where often people get mixed up. So we're going to focus in on x for a moment, and we get 12y minus 8xy minus 3y squared. And the hardest part about partial derivatives is you have to change focus a lot. So now we'll do y, y, y. Let's write that out. So I'm getting 12x minus 4x squared minus 6xy. And now I want to know when these are both 0. And this is where the care needs to happen. There's a certain bit of advice. We want to combine these equations, meaning we want to number them 1 and 2. We want to take one of them and substitute into the other and get it down to one variable. That's always the plan. But there's some bits of advice. And the biggest one is this. And it's particularly important here. If there is something you can factor, it's almost always better to do that immediately. And in this case, there's something you can factor. Do you see that? In fact, in both of them, there's something you can factor. If you don't factor, it gets really big, and I've seen it kind of, yeah, you can factor. So you start to look for what they have in common. This one has a y in each of these. This one has an x in each of these. This one also has a 2 you could factor out if you want to factor out whole numbers. So in my mind, I'm thinking, hold on, I saw that they factored. So before I get into the weeds of solving, let's factor out a y, 12. The little question mark is just for me saying, this is what I'm trying to do. Let's take out a 2x for fun. So divide by 2x, 6 minus 2x minus 3y. Okay. So I think there's there's several that's an important thing we did there that will save us dramatically. So now let's followed the tree method. So equation one, there's two ways it could happen. You could also start with equation two. Either y equals zero, that's one way it can happen. This is why we like to factor. I always say this is the worst magic trick in the world. I'm going to hold two numbers behind my back and tell you that the product is zero. That means at least one of them is zero. So either the first thing is zero, y is zero, or the second thing is zero. And the strategy is then for each one, substitute that into equation two and keep going till you have your critical points. But this question is not asking us to find all the critical points. It's asking us to find the dimensions of the biggest box. So because of that, we can shorten our work a little bit. Which one am I going to ignore? I'm not going to do y equals zero. Not because it's not an important critical point, but because it's not a very good box if y is zero. So y equals zero is not going to be the answer to my question because we're trying to find a box that looks like this. Similarly, x equals zero is not going to be my answer. So the truth is, I could have eliminated these back here and said, those are not my answers to the thing I'm trying to find. So then maybe that was a challenge. Okay, so I have 12 minus 8x equals 3y. Y equals 4 minus 8 thirds x. So I was preparing myself to substitute into equation two. Here's equation two. Let's shove this in here. You can also do it by simplifying side by side. This is our goal in all critical point problems is to get it down to one variable. So the moment I'm here, I'm like, okay, I got it. I'm done. I'll just take the partial credit from there. Let's finish it. So it's going to be 6 minus 2x minus 12 plus 8x equals 0. So I'm getting 6x equals 6. Made up question. X is 1. And now becomes the moment for conclusions. So there were a couple little moments in there. Is that all right? Questions on that part? Okay, let me look here. You typically then are doing some back solving. You need to plug that one in everywhere. The easiest place would be here because then you get y is 4 minus 8 thirds, which is 12 thirds minus 8 thirds, which is 4 thirds. And then once you know those, you should be able to go back and get z. What was the question asking for? Um, you'll notice I never read the question. Find except one vertex that is on the find the dimensions. Okay, the dimensions. So I found that, I found that. I need the z, and I have it. What I don't like about this question is kind of messy to do the second derivative test. It's not terrible, but um, are we good there? Somewhere, the other thing you can search for is if you go to my channel, you can search for volume, I don't know, under a plane. I probably have a video where I did it. There it is. Oh, here's me doing it here. So if you want me to do it some more detail, it's here. If you want to just see a dumb visual of it, there it is. Teaching here too long. All right. Thank you. Somebody's asking a question privately. Do we need to know how to read contour maps or interpret the mixed partial? Um, it's hard visually to ask about the mixed partial. You had that one homework question, so I would know that one homework question. Um, for contour maps, I would just generally know. So my answer to those two questions is not going to be satisfying, but I'm gonna have you look at the homework. For applied optimization in recent years, I've decided that on a test, and this may not be the way on the final, but on my midterm, is I don't ask for the second derivative test. So I wouldn't ask this now. So I always find on the midterm there's not enough time. And so for an applied problem, I just want to see setup and finding the critical points. That's just for my class. Um, but I want to see setup, I want to see finding critical points, and then stop um, for applied max and min. So I think we did an applied max and min. And I'll go till five. If you aren't sick of me, but you can go at any time. What? So then I have a question on spring 19 3B, spring 25 4B. I think we haven't really done double integrals yet. So I would like to do a double integral. Is one of those a double integral question? Is the person who has spring 19 here? Or does somebody else have a double integral question? Let's take a peek. Spring 19 3B is a double integral. In fact, there are two lovely double integral questions on that page. So this is spring 19. I'll make this a little bigger. Hmm. Okay, so let's look. Let's do part A. Part A wasn't asked, but hits another topic that we haven't done yet today. Find the volume of the solid in the first octant bounded by the parabolic cylinder. I find that sometimes these words throw people off, and this is a good example of don't let the bright lights distract you. The name is actually meant to help, but as I like to say, no good deed goes unpunished here. So that usually is what people ask me about. But what's important is first octant, parabolic cylinder, y equals 3. So one thing we've been trying to do, especially in my class, the last three lectures, we started class with something like this. Can we decipher it and run this through our double integral tool? The only problem with our double integral tool is it isn't set up for every problem. We have to do the setup. So we have to find a region on the ground, whatever that might be. We have to find the surface. The surface goes here. The region on the ground goes here. So that's what we're searching for. Um, Brandon, I might put that on my note sheet, just if it might help you visualize. But there's a lot we can do in a problem like this without visualizing. So let's take the robot approach here, and then we'll interpret at the end. So the robot approach is, what is Z? Are there any Z's in the problem? Technically, there are more than one because first quadrant means X is greater or equal to 0, Y is greater or equal to 0, Z is greater or equal to 0. So it's a big, long list of equations. Okay, there we go. There's our list of equations, our bounding sides. So the only thing, there's two Z's, but the only one that actually is not 0 is this one. And that means I'm doing the volume under here if I'm using Z as my output. So that wasn't so bad. Then we draw a region. Oh, we're losing people. They don't want double intervals. Okay, so here we, here we go. So let's go here. X, Y. And now we're going to graph the things they gave me. Y equals 0. Got it. Y equals 3. Done. X equals 0. Good. And then you go, wait a second. There is no region. So we just draw the given XY equations. We did it, but it didn't give us a region. So we are sad here. Yeah, so the other part is this part B, right? So we have this other thing of, well, if that's happening, either the person who wrote this question screwed up, which could have happened because it was me, or there must be an intersection. So find when the z's intersect. And the z's are here. So the z's intersect when this is 0, and so that's when squared, it's when x is equal to plus or minus 2. I think that's why when I wrote this test, I said parabolic cylinder, because I wanted to help if students wanted to realize that they had a parabola like this that extended out, and that might have helped someone do the problem. Again, I don't think it did. I think it hurt people, but it wasn't my intention to hurt anyone. Um, that the thing actually hits the ground out here at x equals 2. So that's why it stops at 2, because the intersection happens here. Anyways, that was the hidden bound in this problem. Now we're ready to go. It's just a rectangular region. You could do it either way. I'm going to put the 3 on the outside because it's a bigger number than 2. 12 minus 3x squared dx dy. Also could do it the other way. So this is a good illustration of both things you need to do when you're drawing your region. We good on that one? So this was like half of a speed bump we found the volume of. I'm going to move to part B, which is what the question actually was. But this is kind of what I worry about is these little moments during the test where you're like, hold on, that didn't give me a region. So I've been trying to get us to experience that as we've been going through. Good, good. Thumbs up. Okay, thank you, Alina Alexander. Okay, so then we have this polar question. Well, the word polar doesn't appear, but it's definitely polar. I shouldn't say it's definitely polar. You could probably do it without polar. What about the plane z equals 3? Oh, there wasn't a z equals 3, it was y equals 3. Y equals 3 was here. Yeah, there's actually this plane that like sticks up like this. Yeah. Okay. So then this one was, so we're still talking about spring 19. So several things point to polar, but the biggest one is that there's a circle centered at the origin. The less nice thing here is that we have another circle. Now, at first glance, that might not look like a circle. So I'm going to make a few side comments here. This is a circle centered at the origin. This is a circle centered elsewhere. The question didn't ask for this, so this is a side comment. If you want to know where this other circle is centered, you got to move everything to one side and then use our little maneuver. Half the middle squared. And that gives us the following. So this circle is actually centered at 1/2, 0, and the radius is a half. I say that because sometimes in the homework, sometimes you were given something that looked like this, and sometimes you were given something that looked like this. And they're actually the same thing. But this test question was being nicer to you because I would rather have it in the form above. The one in the bottom is good for graphing. The one up here is good for converting, which is what we're going to do in a moment. So just a comment that if you had to graph it, um, you would need to do that completing the square stuff. So I'm going to leave that. That wasn't really part of the question. Okay, so I need to describe this region. You could do it as a top bottom region, but you're gonna have lots of square roots. Really hard to do as a left right region. Pretty nice as a polar region because we have a starting angle, we have an ending angle. In between, you're always between this on the inside, that on the outside. Inside, outside. So we need to figure out what these are, what the pattern is, and we need to figure out the starting angle and the ending angle. Once we've done that, then we put all the bounds in there and we go. So step one is already done. They already gave us the intergrad. Step two is to draw the picture. They've already done that for us. So this becomes labeling our picture. All right, I'm going to get rid of this here. So the moment I make the decision to do polar, it's probably a good idea to immediately convert. So convert those two things to polar. So this one gives me r equals 1, or the square root of 1. This one, though, doesn't do that. It gives me that r, I should have said r squared is 1. This one gives me r squared is, what is x in polar? Yep, r cosine of theta. And so that looks funny if you haven't seen that. But since this has happened a couple times in the homework, we have a little bit of a plan here. I'm always hesitant to divide by r. The truth is I don't do this in class, but I'm very tempted to move everything to the same side and factor. I don't like to divide by a variable because I'm worried I'm dividing by 0. So if I was doing this problem, I probably would do that. And then I would say, well, there's two possibilities, either r equals 0 or r equals cosine. But r equals 0 means you have a point at the origin. So the distance is r equals cosine. But since I've done a lot of these, you can also do it by dividing by r. But I have seen that throw people into a spin before. I've seen people get stuck solving that. But it's cosine of theta. And cosine of theta is how far it is to this circle. So what I just solved for was this distance. From here to here is cosine of theta. And that's going to be true no matter what the angle is. So that's the conversion that had to happen. How far is it from the inside to the outside? What's that green length? I feel like every question I've asked today has this same answer. It's 1. Yeah, so this is r equals 1. If you go somewhere else and start walking out, this is cosine of the angle, and the outer one is still 1. Okay, so that's the key you had to realize is that You had to convert. You had to realize this circle became, this is probably the hardest part, that this became cosine. And then you could say for all the angles between 0 and pi over 2, the inside is cosine of theta and the outside is 1. And then we're going to convert the rest of this. So that's the same as 3 times r. And then you hate to drop the ball at the last moment, so dA is r dr d theta. Yes, the completing the square part was not necessary here, unless you didn't have a picture and you had to make the picture yourself. I mentioned that because sometimes when you looked at the homework, sometimes they gave it to you in this form. And some, if you look through the homework, there was one where they gave it to you in factored form and one where they gave it to you in expanded form. And I just wanted to comment that they're actually the same. Um, yeah, good question, Brandon. From there on out, it's computation. But that doesn't mean it's easy. So this is going to be r squared. So when you integrate, you're going to get r to the third with a 1/3. So that's kind of nice. From cosine of theta to 1. And so you get the integral from 0 to pi over 2 of 1 minus cosine cubed of theta. So there is a little challenge here. I'm going to split them up and try to figure out what to do with this cosine cubed. This one I know is going to be theta, so it's just going to be pi over 2. This one, how do you integrate cosine cubes? That's probably the hardest integral on this test. It's not really that hard, but you have to know, have a plan. If you have even powers of sines and cosines, you have one strategy. And if it's odd powers of sines and cosines, it's a different strategy. So what's the strategy here? It's U sub. That's it. We're going to set up a U sub. How do we set up a U sub? We yank one of the cosines out, and then we turn everything else into a sine. Yep. And so because after you pull one cosine out, you're left with a cosine squared. And this is why it works for an odd, because when you take one out of an odd, it becomes even. And when it's even, you can use this square identity and you get 1 minus u du. Impress your friends and change the bounds. You put a 0, you get a 1. So it's pi over 2 minus u minus 1/2 u squared from 0 to 1. So it's pi over 2 minus 1 minus a half. So it's pi over 2 plus a half. Again, don't trust me. Please check solutions. All right, how did we do there? So we did a polar. So we got some double integrals in. Let's go back. Questions on that one before we depart from this page? Just watching the chat. Lovely. Let's go back here. How did we get r cubed? Good question. Let's see. This is, now I've forgotten. Spring 19. This one. I had an r squared here. There was an r because this was r, and there was an r because of r d theta, so it was r squared. And when I integrated, I got 1/3 r to the third. Yeah. Lovely, great. Okay, so I'm gonna call spring 19, 3A and B, double integral setup, and then we did 3B was polar. Look at that, we're hitting most of them. Uh-oh, I made the chat vanish. And I'm going to call that one, darn it, that one there. So I'm happy to look at these other ones. There's a spring 24 4B. Oh, I think you said somebody commented on here that this was also a polar. So maybe that's a good one to look at. So let's do a quick back and forth. Um, Give me first step in the chat. Partials, that's it. Partial with respect to x, partial with respect to y. You're going to give the tangent plane. So that's what we're after here. The tangent plane is a linear approximation. This approximates what that value is. Oh, implicit. Darn it again. Differentiate. Find and classify critical points. So that'll be a chance to find the partial derivatives. Plug the first. So, yep. Linear approximation. Sometimes it confuses people that in the book they call this L of xy and they move this to the other side, but it's still the same equation, whether we move the thing to the other side or not. So to me, the two words, linear approximation and tangent plane, I guess those are two words each, are the same. Linear approximation is the way to think about what the tangent plane gives us. Yeah. Um, Find and classify critical points. Oh, a few people have asked this on the discussion board. Closest. So this is a minimum distance problem. But the question is about force, so maybe we can come back to that. Set up a double integral, reverse the order, volume, one loop of the rows. Is this the one that was asked? Are you still here? All right, thank you. This is more about a fact about polar. The moment it says area of one loop, these are the problems where we're using a double integral to find area. The double integral of one is the area. Step two is we draw the region, done. Step three is we give the bounds. So these questions that are about a loop are really about understanding when does a loop start and end. You don't have to be an expert on roses, but what does it mean to start and end a loop? It means something very particular. In polar, we have to think about what does it mean to be at that spot. I'm trying not to say it. So in order to do this problem, we're going to need to figure out where we start, meaning what angle this is, where we end, meaning what angle this is, and where the inside and outside is. Now, since this touches the origin, the inside is, oh no, I'm about to say it. I'm really trying not to say it. So when I see this question, I see one loop. It's about when R is zero. That's what this is about. So when I think about polar, and we're for the R purposes in this course, the most important things if you're just trying to plot are angle zero, angle pi over two, angle pi, angle 3 pi over 2. And in polar, those are like our intercepts. We're going to look east, north, west, south. So in polar, usually the first thing you do is you think about where those are. For example, you could even do this here. You could plug in a zero and see that this is a one. Okay. The next most important thing when it comes to polar is to figure out when R is zero. Because when R is zero, that means you hit the origin. Why didn't we have to do so the question that we did earlier with the rows in a circle, good question. Can I remember which one that was? Here. So the reason I didn't figure out where the loop ended, somebody's asked me a question about this here. The loop ends right here, but that wasn't part of the region we were talking about. We instead of finding when R equals zero, we found when R equals one, because that's going to be when it intersected. That's when you stop. We weren't doing a full loop, yeah. Um, this one is doing a full loop. So we want to go all the way until we hit the origin. So to me, this kind of adds a little layer to our understanding of polar. Sort of polar level one is to know how to graph the intercepts. What does it mean to be up, down, left, right? That's this. Polar level two is to know when it hits the origin. And then we can refine things a little more. So yeah, when I see one loop, my job becomes the following. When is this zero? That's when the loops will start and end. The only challenge is that happens a lot. So now I have to think in my head, when is cosine of blah equal to zero? So then I think about my unit circle and I go, well, that happens here and here. That's when the x coordinate on the unit circle is zero. So my next step is to write 2 theta equals, this is my own little style, but I start writing those. I tend to like to write the first positive one, and then I like to go back to the first negative one. And then I could keep going until my hand's tired. There's a lot of answers. Pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2. There's a whole bunch. And so what I do is I say those are the ways that this can be zero. And then I divide everything by 2. I say the only way that can happen is if the angle is this. And that gives all of these angles. We might have been able to guess that already because it does look like the angles when it goes to the origin are pi over 4 and 3 pi over 4 and 5 pi over 4 and 7 pi over 4. So that was the key challenge was the bounds are negative pi over 4 to pi over 4. And then we need inside outside. So we need to know for any one of these little things I've drawn, I'm in the region right away. That's R equals 0. And then when I'm on the edge, that's the edge of the rows, which is what R equals cosine of 2 theta is. So this is 0 to cosine of 2 theta. And it's easy to mess this up because you go, well, there's supposed to be a 1 here. But even when there's a 1, you always have to talk like a pirate when you do polar. R already theta. Divyan, does that answer your question? Lovely. Lovely, lovely. There's going to be another half angle there when you go to finish it. Um, That was this one. We're going to say spring 25 4B polar with a loop. Uh, where the bounds are. Somebody's asking me about bounds on a double integral. Could I ask a homework question about polar? We could. There was one question on somebody else's exam. Is that person still here? Fall 23's Yishu Zhu's exam. I feel like I've been asked that in previous quarters. I don't remember what it is. If not, I'm going to switch to Ketki's asking about a homework question. Yeah, what's the homework question? Let's do that. Somebody was asking about a homework question. So for the most part, this is it. I'm going to stop here and but we can do. I have a little bit more time if we want another question. This will continue tomorrow. Professor Nishifer said that she is going to do a review from 3 to 5 in our room, Kane 210. So I think it's just drop in, ask questions. Um, but is there a homework or exam question? There's a question on, so there's a 15.3 number 11. So then two questions came in, 15.3, 11, and spring 18, 4B. Spring 18, 4B, I'm going to guess here. Make sure that you look at the top of the question for the function. I'm going to take a quick peek to see if I'm thinking of the right one. Wait, spring 18, okay, here, 4B, and then we'll look at that homework question. Always good when you tour to look, okay, partial derivatives, find and classify critical points, absolute max and min. Okay, it's not what I'm thinking. Volume, volume. Okay, I like this. We can do, is this it? Spring 18, question 4B. Is that the one? Yeah, this is also similar to a homework question. This question is not so much about polar, and it's more about can we draw this? I mean, that's how I do. Anytime that someone says reverse the order or rewrite, it's really a question about can we draw the following? And this is how we read this. So this is a fairly quick question, so I'll do it and then we'll talk about a couple of those homework questions people are asking. So they're telling me that y is between here and here. Those are like, I like to think of those as our tick marks. We have a tick mark here at 0. We have a tick mark here at the square root of 2. So think of the outside as the tick marks. You can even, if it helps, think about how everything is in terms of y. So what I'm about to draw is left and right. If that helps you. I mean, I don't always think of it that way myself, but those are the tick marks. Okay, so the things you actually need to draw are the bounds. And the bounds are the following. X is between y on the left and this on the right. So we will be able to finish this question if we can draw the following two things. So we need to draw that, and we need to draw that. Now, if we have trouble drawing y equals x, we can rearrange it into the other form. Sorry, I said X equals Y. Um, and this one I recognize. This is the right half circle, but you could rearrange if it's helpful to realize that it's a circle. But it's the right half circle because it's the positive x's. Okay, so I'm going to now erase this and say you didn't do it the way I did it. A common issue that students have on this one is they draw this circle, they draw this line, and then they're like, do I shade this? Do I shade this? Do I shade this? Do I shade over here? Do I shade here, 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 here? But there's a confusion about what do I shade? And that's where the knowing what that we're doing left and right and knowing where the tick marks is, it's to me this one is easy to mess up. I know I've done it before where I shaded the wrong side. And so what you can do is you can even test points, but I know from this that I'm not going all the way up here. Not going all the way to two. I'm only going to square root of two. So that already is a little hint. But I also know that the line needs to be on the left and the circle needs to be on the right. Okay. So I think that's the hardest part of this one was to realize the region in question was this region. And if you were to walk out to it, this is x equals y, and this is x equals the square root of 4 minus y squared. Okay, so once you have the picture drawn, you're done. Why do I say we're done? Because now it's fairly quick to do in polar. The bounds are, somebody said in the chat, 0 to pi over 4. The inner bounds are, if you walk out, it's going to be 0 to 2, I think is that radius. And then x squared is going to be r cosine of theta squared, r already theta. So this sort of emphasizes that this question is really about draw the region, then give the bounds. Is that all right? There's still some work to do in computing. Let's go take a peek at some of the homework, since that was a few of you asking that. Spring 2018 for B. Um, I'm going to call that, it's a reverse the order type question, polar version, polar edition. Okay, so now let's look at the homework. I think I have it at the ready. Homework 15.3. Number 11 came first. Let's take a look here. I think part of the issue, I think it's easy to be uncomfortable with what it's asking, like hard to visualize. Um, it does follow our recipe, meaning you can solve for your z's, you can find the intersection, it will work. Um, but I think under, when we talk about a cone, this is this cone. And we have this, be consistent in my coloring. Here. Well, that's the upper hemisphere, but. So the question says above this cone and below the sphere. So if you think about that, the lower hemisphere doesn't come into play in that description. And when I picture it as a snow cone. Who's had a snow cone? So what we're going to do is try to figure out the region. So I'm going to do, when I look at this question, I go, okay, I need to compute the volume under the cone. This is the solving for the z's. And I need to compute the volume under the sphere. So I'm going to solve for this z, which gives me this. I'm going to find this volume. I'm going to find this volume. And then I'm going to subtract. So that works here, just following the recipe. But the question is, where do we stop? We stop when they meet. And I intentionally did not draw them on top of each other, but if you drew them on top of each other, they run into each other. And when they run into each other, you get this intersection, which is like right here. That's the region we're integrating over. But let's do this. I don't know that I should do this, but I'm going to do it anyways. Here we go. So we are saying upper cone. There's our upper cone. Let's make it so we can see through these things. There. Would look better in green. Lovely. And then z equals the square root of 1 minus x to the second minus y to the second. Is that? Ooh, it's way in here. So we're doing the volume between those. But in order to know when to stop, I need to know when they intersect. So let's come back to the visual in a second. When do these things... So normally your next step is to draw the region on the ground. And that usually involves first graphing any given x and y equations, which there are none. And then the next step is finding when these intersect. And so these intersect when x squared plus y squared. So one thing I like about chapter 15 is we're really using the same thing every time, but each problem gives us a little more depth into understanding of that process. So it's x squared plus y squared plus x squared plus y squared equals 1. That's actually a circle. So 2x squared plus 2y squared is 1. X squared plus y squared is a half. So that's a circle of radius square root a half. Not very nice. Okay, here's how I would use that visually, just because I want to make a visual here. So I'm going to draw a circle of radius square root a half, 1 half. Let's make it red. How about orange? I feel like this should just be on the ground. I'll leave it like that for a second. That's the region on the ground. If I were to draw it up where they intersect, um, let's do this. So this is where they intersect, right here. That's the intersection we found. In fact, I don't really need to worry about beyond that. So I'm going to do something interesting here. I'm going to say I only want to look at the cone inside of this circle. Ah, that's better. Now I'm not looking at the whole cone. And I only want to look at the sphere inside this circle. Ah, that's better. There it is. There's our snow cone that we're finding the volume of. And we want to do it all above here. Not there, here. So we're actually doing it above here. So that's the problem we just figured out. We're going to do the volume under the green, the volume under the blue, and subtract. If you don't know what I mean, here we go. Oops, didn't mean to do that. So we're going to find the volume of, oh, it won't let me do this. Oh, yeah, it will. We're going to find that volume. That's the volume under the cone. And then we're going to find the volume under the sphere. That's this weird thing. So we're doing that volume minus this volume. So I don't know if any of that helps. Okay, so that's the point of that is we find the intersection so that we have this, and now we have two jobs to do. We're going to do the volume, so 0 to 2 pi, 0 to square root of 1 half. Square root of 1 minus r squared, r d theta. That's the volume under the sphere. And then we're going to do integral from 0 to 2 pi, the integral from 0 to square root of 1 half of r times r d theta. That's the volume under the cone. So you need to compute these two volumes, subtract, and done. So it's kind of daunting when you look at the description, but it does fit our recipe of find the z's, find when they intersect, draw the region, integrate, subtract. Does that help at all? I kind of ran through it quickly, but yeah. So there's a question on number 7 and a question, two different sevens. Do I have this 7? And I don't know if Owen's still here, but 14 4 number 7. Are you still here, Owen? You might have stepped away. No, you're still here. Uh, this was more of a conceptual question. I mean, honestly, this is more of a what would I call this? Almost like a 13 2 question. So this question said find the equation of the tangent plane, but you did not have the surface. And so this question required you review how do we find the equation of a plane? Oh, are you still here? Yeah. So this one's a little different. So normally, just to sort of recap before I do that question, when the question says do a linear approximation or it says do the equation of a plane, tangent plane, you're pretty much doing derivatives. The derivative with respect to x, the derivative with respect to y, -8 over 1 minus 8 x minus 8y, and then you're plugging in your points and you're computing. But when we're doing those, we're using that shortcut formula of we actually have the function. So this is back from earlier homework. This question, you weren't given the function, so you couldn't do any of that. So you were back to kind of square one. And square one, when we find the equation of a plane, is we need a point and a normal. And typically the way we find a normal is we find two vectors on the plane and we do their cross product. So that's why I say this is less to do with tangents and more to do with reviewing how we find planes. Okay, so the actual story was we need two tangent directions. Because the tangent plane has all the tangent directions. So if you're on the tangent plane and it's touching a surface, every single tangent line on that surface is on the plane. So if you can find two of the directions that are tangent, you can take their cross product and get the normal. This is partially related to what we did in 14.4, which was that's why we can get away with just knowing the slope in the x direction and the slope in the y direction. But in this case, we don't know those. So what did they give me? Well, they gave me, so let's pretend this is our surface. They gave me one curve that's moving along the surface, and they gave me another curve that's moving along the surface. And then they gave me this point. Now, if the curves don't go through the point, the problem really wouldn't make sense. So they gave me two curves that go through that point. So the strategy on the problem was to get a tangent vector from each. So it was really about finding the derivative and the derivative, and then doing their cross product. So those would be two of these vectors on the plane that we're trying to find. Okay, so but the problem was if you just took the derivatives, the derivative of the first one is 3 negative 2t negative 5 plus 2t. And the derivative of the second one the problem was you had to plug in something for t and u. So I remember working with a few students on this one. I think a few different confusions. One was, oh, we have to take the derivative, yeah, because we want two tangent directions on this surface. But the other challenge is how in the world do we find t and u? And that's why I say this feels a lot more like this is kind of a combination of 12.5 and 13.2. So it's a bit more of a review question. Kind of would be better for a final, but um, how do we find the time when those two curves pass through 3, 1, 4? So we have some side work to do. And the side work is when does this curve go through 3, 1, 4? And when does this curve go through 3, 1, 4? They're not necessarily at the same times. I think this one is at 0. I can see it right away because there's a 3, 1, 4 already there. The other one, let's see, if this is a 3 and this is a 1 and this is a 4, U has to be 1. Because the question, so somebody's asking a private question, why aren't we doing cross products of the positions instead of the directions? Because the question wants the tangent plane. The tangent plane is the plane that contains all the tangents. So how do I say this differently? So if we had a surface here and we have a point there, part of the problem is we write the position as a vector, but you have this point, and let's draw this. When we write R1 of whatever it is, 0, it's this vector that points to this. If we do R2 of 1, it's the same vector. They're right on top of each other. So R2 of 1, these are the same. If your goal is to find the tangent plane, think about what would happen if you do the cross product of two vectors that are the same. Does anybody know what happens if you do 1, 2, 3 crossed 1, 2, 3? And you can actually do it fairly quickly. 6 minus 6 is 0. 3 minus 3 is 0. 2 minus 2 is 0. And that does not give me the normal for that plane. In order to get the normal for the plane, you need to do the cross product of two vectors that are on the plane, not pointing to the plane. So we needed tangent vectors for the curves, not positions. But it was really because they asked for a tangent plane. We pretty much never use the original positions if we're thinking about the direction in which something goes. A very similar thing happened on our exam too, when it was a question asked for the angle of intersection. That means the angle between their directions. So anyways, this question was about plugging in 0, you got 3, 0, -5. Plugging in 1, you got 2, 6, 2. You did the cross product and that told you what these were. But I would argue that that's a little more of a, it doesn't really fit in with what we were doing today, but all right, any last things here? Checking my time. To take a son to a baseball game shortly. Oh, most of these messages were private messages. Now I see. Okay, I think I'm going to call it a day. Go ahead. Is there a question there? I thought I heard something. All right, have a good luck with all your other things. We'll review tomorrow in class. Feel free to welcome to visit uh, Professor Nishifer's review tomorrow, and let's have a good exam on Thursday. Lovely. Stop. Exit.